The last type of geometric transformation we'll talk about is one that sadly is not really discussed in high school math very much at all, and that's the shear. So we just have to get used to this, discuss it a little bit. A shear, and of course you'll either shear along the x-axis or along the y-axis. Let's start with the x-axis. It's a transformation in which each point of the plane is moved parallel to the x-axis by an amount that is proportional to its distance from the x-axis. This distance from the x-axis is the y-coordinate. So the greater your y-coordinate is in absolute value, you're going to see more change for that pre-image point. The constant of proportionality that we're talking about will be designated by a number k. So, for example, we could say that the image x prime is x plus, and then there will be some real number like a 2 times y. Y prime, the new image of our y-coordinate, is going to be identical to the pre-image of the y-coordinate. So the y-coordinate is fixed. The y-coordinate is not going to change. The x-coordinate very well could. So let's see what this transformation matrix would look like. Obviously, with a 1 and a 2 here, you'd expect to see a 1 and a 2 here. Here we have a k, though. That'd be a 1 and a k. There's a 0x plus 1y down here, so we'd see a 0 and a 1. That's just the relationship between the matrix multiplication. But really what the author wants you to see here is that a square is going to be changed. It's no longer going to be a square. It's going to shift to become a parallelogram. First, notice that if your y-coordinate is 0, that is, if you're on the x-axis, you're not going to change at all. And sometimes students are wondering why that is. Well, look, the k times y, if y is 0, of course, we're not going to see that k times y being any real change for the image of x prime. But the higher up we move, like let's say we are at 0, h, we can see that x prime would be the x-coordinate plus k times h. So our new x-coordinate would be a kh. That's what we're seeing right here. Remember, the y-coordinate remains the same. What if we had h comma h? Well, plug in an h for your x, plug in an h for your y. You'd get h plus k times h. And that's exactly what we're seeing right here. So we're seeing the shifting off to the right here. This is what a shear is called. You'll notice that the base is still going to be the same. The bases on the x-axis, at least, are going to be preserved, aren't they? The height of the figure, the distance from the highest point to the x-axis, well, my goodness, that's the same also. Area in a shear is preserved. Congruence is not, of course. Obviously, this image figure is a parallelogram, way different than the original square. However, area will be preserved. The author has a little picture of a camel, what the camel could look like being sheared. You could see that the area, though, of the figure would be equivalent. Just as you can shear along the x-axis, you could also shear along the y. The big difference is that the x-coordinates now are going to remain fixed. The y-coordinates are going to be the old y, the pre-image y, plus some constant multiplied to the pre-image x. So I think the best thing we could do, because this is something sadly that we really don't have a lot of experience on, I think the best thing we could do is go ahead and work some problems out and definitely get a little more familiar. Skip number 1 just for a second. Let's do number 2. We have the ordered pairs -1, 0, 1, 0, and 0, 1, which happen to be a triangle. Now, if we plot those points, we'd be one step left, one step to the right. 0, 1 would just go one step up. So here are our 3 vertices. By the way, I'm going to find the area of this pre-image right now. The base, how far is it from -1 to 1? Well, it's 2 units. One step from the origin to the right to 1, 0. Likewise, going off to the left. How about the height? Well, it's 1. You can see from the base we're rising up 1 step. You can see very fast that this area is 1. Well, where are these ordered pairs going to be sent? Well, we've got x prime is equal to x plus 2y. So x prime is equal to x plus 2y. Remember, the y coordinates are going to be the same, right? I've got 0, 0, 1. I can immediately say, look, the y primes, the image y coordinates, they're not different at all. But let's very quickly find out what's happening with our x primes. X, the old x coordinate, plus 2 times y. Well, -1 plus 2 times 0. Well, that's just going to be -1, right? When your y value is 0, 2 times 0 is 0. You're just left with the same pre-image x. Look, 1, 0, same thing. You'd have a 1 for your x. 2 times 0 is 0, so you just have a 1. Now, at first glance, you'd say, well, this is kind of ridiculous. You're not changing anything. Well, like I said, points on the x-axis remain fixed on the x-axis. Here's something different. 0, 1. Well, now we're going to see a change. X prime would be our x plus 2 times 1. Well, 2 times 1 is a 2. So what's happening? We've got -1, 0. We've got 1, 0. But then we've got 2, 1. Yes, it's still a triangle, but it's certainly not the triangle that we first thought that we began with, is it? You can see that this top point, 0, 1, has been slid over considerably. It's moved over quite a bit. And that's what I mentioned before. Your y coordinate really plays a huge role in these types of changes when we're moving along the x-axis. The larger the y coordinate is, the more movement we are going to see with that image. But let's examine the area. The area, we'd say, well, it's 1/2. What's our base? You'd say, my goodness, my base is still a 2. And would you look at this? Even though it's now an obtuse triangle, you could see that my height, the distance from the highest point down to the base, extending the base, is still a 1. Area is preserved. By the way, that's what they were asking us in number 6, to show that even though this image triangle has been sheared, it's being slanted over, and it's no longer congruent to the original figure, it still has the same area as the pre-image. A follow-up question, can T be sheared into a right-angled triangle? Well, how about we took this point, well, obviously we'd have these points fixed. What if we slid over just above? Indeed we could. Could this happen? Yes. What would it look like? Well, I'll leave it to you to confirm it. It would be x plus 1y. And over here, oops, well, tell you what, let's write it as a matrix, so sorry. Let's write it as a matrix. There you go. So look at that. If your constant k was a 1, you would see very quickly that the point 0, 1 would be sent to 1, 1, and then we'd have a right triangle. All right, well, let's take a look at problem number 3. What happens to a parabola, y equals x squared, under a shear? And what a fantastic question. I think many of us can envision what's going to happen. You might think that the parabola is going to be opening up now on a slant. And it might look a little odd. And, could we find the equation of it. I think maybe that's even a more challenging question. Maybe the author originally was just getting kids to try to envision what the shape is. Let's do even more than that. Let's try to find the new equation. And right here is such an important skill. I want us to write the transformation matrix. In other words, the shear x plus 1/2 y over here, we have a 1x and a 1/2 y. Over here we have 0x plus y, a 1y. Hopefully you can see that that definitely is the case. What I need to do is to solve for just what x and y are. I know what my x prime, y prime would be. But I'd like to find x and y so I could substitute that into y equals x squared. Well, tell you what, when you want to eliminate this transformation matrix, what you do is you multiply on the left by the inverse on both sides. And again, I've brought that up before. I'm going to keep bringing it up because this is going to be such an important skill very, very soon. We're going to be using this all the time in the future. So just as you would multiply by the inverse of a number to eliminate that in a simple algebraic equation, the inverse in a matrix multiplied to the identity matrix, and the identity matrix would just multiply any matrix to itself. So we're just left with x, y. Notice we can't divide both sides by a matrix. But now what? Well, on this left-hand side, tell you what, you could type in the inverse on the 89 and let your calculator get that for you. If you did, you would get this. Multiplying through, you would get the following. You would see that this would become x prime minus 1/2 y prime. Down below, you'd just be left with a y prime. 0 times x prime cancels out. What are we getting at? Well, most importantly, now we have equations for the pre-image. We have what x is equal to and what y is equal to. And for number 3, what they're really asking us to do is say, how has y equals x squared been changed? Well, y is going to be y prime. X, we can see, is going to be x prime minus 1/2 y prime. And we're going to square it. So this is how the parabola is going to be changed. Now at this point, just expand. And you know what? Let's drop all the primes. I think that might really help out. Look, this will become x prime. Double your middle term. If you double a negative 1/2, you just will have a negative 1. So you'll have a negative xy. And then we'll say plus, squaring our last term, 1/4. And then we'll get y squared. This is the equation of a parabola that has been sheared. And of course we could bring the y over to the other side, set it equal to 0 if you'd like. Looks a little different, but this is what we have. So we're almost through with this lesson. We're going to have to pick it up again to finish off number 4 and actually number 5. And hopefully this will get more and more comfortable. Just down the road, letting you know, we're going to deal with all of these transformations at the same time. You'll have a shear, a reflection, a rotation, a translation. And we're going to learn how we can quickly find equations for x and y.